Okay, so good morning everyone. I am Michele Di Lauro and I come from the Center of Translational Neurophysiology of Speech and Communication in Ferrara, which is held in this beautiful historical place. It's a center from the Italian Institute of Technology, but as a background, I am a chemist. So this talk is going to be the story on how does a chemist be useful for the neurophysiologist community and for the medicine community, and how this is made possible by the physics of condensed matter, and in particular by the physics of organic semiconductors. So I will tell you a bit about my story, okay? So first of all, I'm lost in translational. Okay, this is a word pun, but it's great because what we do in our center is to work to develop translational technology. So we want that everything that we develop is capable of being translated to the human being in clinical scenarios. Okay? And translation by itself, by definition, as Sofia Coppola, the director of this film, said, is the story about things being disconnected and looking for moments of connection. And this is what we are doing with, let's say, with organic electronics, because we want to bridge a gap which is between the biological world and the electronic world. Okay, so integration between electronic devices and living matter, in our case, the central nervous system, requires bidirectional communication. But there is a lot of mismatch, because there is a mechanical mismatch, there is a structural mismatch, environmental mismatch. The carriers are different. The time scale are incredibly different. So we want to bridge a signaling gap between the living matter, let's say, and the electronics. Can we bridge it? Of course, this is not an idea of mine. We can do it with organic electronics. I reported here some very famous papers that are dealing with this concept. But the core of this bridging relies in the materials that we are using. We are using these organic mixed electronic conductors. And here I present you P.PSS, which is the workhorse of this field. Okay, it's a copolymer. It's made out of two complementary ionomers. So one is positively charged, is this ethylene dioxide thiophene, and the counter ion basically is this polystyrene sulfonate. Okay, so what happens is that this polymer is neutral by itself, but it has the capability of conducting charge. If I apply a bias, what happens is that I have the transport of positive charges in the polyethylene dioxide thiophene chain, which is counterbalanced by an opposite motion of protons in the polyanion complementary chain. Okay, so the holes that move are dressed with this negative charge that goes along with them, given by the motion, the counter motion of protons. Okay, this is the point. This guy is a conductor. It means that it obeys the Ohm's law. Okay, but what happens is that I can modify its conductivity. Why? How? By intercalating cations. Because if I drive cations in this polyanionic matrix, what happens is that they will coordinate the sulfonate ions, and then the protons will not be able to move, and then the conductance changes. The conductance drops. Okay? The resistance increases, and this behaves as an organic semiconductor, which is the main architecture that we use for exploiting these properties. Is the organic electrochemical transistor or the electrolyte-gated organic transistor, you call it whatever. But the important thing is that in these devices, electronic conductivity depends and varies with ionic concentration, and in this way, the organic mixed ionic electronic conductors can bridge the signaling gap, okay? Also, they are organic. So we are chemists, we can tailor the properties by design, we can make them biocompatible, biodegradable, and also mechanically compliant, let's say. Okay, I was telling you, this is the main architecture. It's the three-terminal architecture in which a channel of polymer between two electrodes, which are called source and drain, has a modulable conductivity, which is modulated by the potential that I apply to a third electrode, which is bathing in the solution, and drives cations into the film. So this is what we are doing. And you see, the ion density in proximity to the channel governs the conductivity. Small gate voltage modification yield great current modification, and the transconductance, which is namely the derivative of the channel current with respect of the gate voltage, is the key operational parameter because it's the gain factor of our devices. Okay, but all these quantities are quasi-static. When we want to approach the brain, we want to collect, analyze, and let's say describe signals that are varying with time. And so the dynamics of the device response and of the material response becomes critical. And typically, our organic devices are very slow, and so we need to always to choose to make a compromise between having a decent bandwidth or having a decent, let's say, transconductance amplification. And so we invented a field in which slow is good, and we called it the organic neuromorphic electronics. Okay, neuromorphic means that your circuit can emulate the signal processing features of the human brain, okay, of a neuron. Okay, but how do neurons work when they are processing the signals? Well, they are relying on kinetic imbalance between the input signals and the output signals. So what is the easiest way to emulate this behavior in organic electronic device? Well, nothing is as simple as that. I take an electrolyte, it has got an iron and cations inside. On one side, I have my organic conductive polymer. If I apply a pulse of voltage, I will cause the ions to migrate, okay? I have this current of cations, which is the displacement current. You know it better than me. And what happens is that when I remove the stimulus, the system relaxes, okay? So if the subsequent stimuli are far enough, so the system can fully relax, and the second pulse arrives in exactly the same situation as the first one. Okay, but if the pulse frequency is too high, the system cannot fully relax. So when the second spike arrives, I have less displaceable cations, so I have a lower current, and I have, let's say, a profile of evolution of current in time, which is a time frequency integration, which is what neurons do when they operate. The entire phenomenon is called short-term plasticity, and this is very useful technologically. Okay, so how can we control this kinetic imbalance? Okay, this is, of course, controlled by capacitance. So it's controlled by device geometry, by polymer thickness, polymer nature, let's say polymer chemistry, and also parameters of the electrolytes. So concentration and eventually specific interaction between some solutes and our electrodes. Okay, so a given combination of these parameters yield one single time constant upon one single frequency of stimulation. But we want to keep in mind the original mission. So we want it to be translatable. And when you are designing a device for biomedical application, you cannot change neither of this stuff, okay? Because in order to get approval from your ethical committee and from your Ministry of Health to put something in the brain of people, you need to define the architecture very precisely, and it cannot change anymore. So we had to devise operational routes to tunable neuromorphic performance without altering the geometry, the thickness of the polymer, and whatsoever. Okay, the materials, and we can. This is the start of our story. It's a quite long story. It started during my PhD, so now almost 10 years ago. And what happens is that we learned at first how to control the short-term plasticity by changing the material. Then we discovered, and this was inspirational, that the time constant of our STP decay profile depends on the concentration of the analytes in solution. And so we used it for sensing after proper, let's say, development of analytical circuit models for our devices. And then we went on because we said, okay, all of these were two-terminal or pseudo-two-terminal architecture, but we are working with a transistor which has got 3 terminals. So let's try to make advantage of all the available terminals in our architecture. And now I don't want to bother you with all the mathematics, but the important thing is that we managed to elicit tunable STP decay, tunable short-term plasticity in our devices, either by acting on the gate voltage offset or by acting on the frequency of stimulation. Okay, so we liked it because we have seen, let's say, that the parameter that the neuromorphic behavior depends on the gate voltage as exactly as the transfer characteristics of our devices. And so we went on. Okay, the important take-home message of this is that we have in our toolbox a frequency-dependent resistor whose dependency on frequency depends on the doping state, which is the resistance. I know it sounds a tongue twister, but it's important to understand this, okay? So there is a complex interplay because we have the dynamic of the double layer in between. So ion dynamics governs resistance, which govern frequency dependency of our architecture. Okay, we went on with this. We tried to change a lot of different connection scheme, and we managed to eventually reach a configuration which one can elicit at will depression and potentiation. We can alter, of course, the baseline current, and we have relative current variation for the doped channel. Most importantly, by setting an arbitrary reading time, we can deterministically predict the relative current variation, which is linear with the gate voltage, and we as physicists, we like linear trends, and so we can bring these small devices, which are memories, we can bring them in different states, and the memory state depends on the gate voltage. So this is very useful. Okay, so now we add a line to our tongue twister, which is the gate voltage, so our main control parameter. But now, what do we want to do with this? Because we are working in a electrophysiology department. Okay, so we are using it to filter electrophysiological data in real time. So this is when we interface our electrolyte-gated organic transistor with a simple electromyography experiment. And you see, these are the spectrograms of the trials of electromyography. This is actually a PhD student holding a weight into his hand with some electrodes attached in his muscles. And this is the average spectrogram, okay? You see the content in frequency is all around 20. Okay, but what we want to do, if we are building a, let's say, human to machine interface, and we are focused on electromyography, we want to isolate this 20 Hertz frequency with respect to all the others. And we can do it. We can do it because with our gate voltage, we are able to increase the relative power of a single frequency band with respect to all the others. So now this is a sorting efficiency map centered on 20 Hertz, so I can transduce the 20 Hertz way better than the high frequency, and also better than some low frequency, which is the discovery of this work. Okay, but now that we have understood that the dynamics of the double layer is a key operational parameter to device filters, now the fantasy is the limit, because we can build up organic resistors, we can build up organic electrolyte capacitors, and we can engineer filters with these guys. RC filters, normal passive filters, okay? And this is what we have been doing lately. So we are connecting electrolyte-gated organic electrolyte-gated organic capacitors and organic resistor in series, achieving low pass and high pass filters. And if we couple these with the electrolyte-gated organic transistor, which is inherently a low pass filtering guy, we can achieve band pass and modulable low pass. Okay, and we can also implement this in, let's say, convoluted architecture, in which we are able to sort a common input signal, but just, let's say, transducing the high frequencies on one side and the low frequencies on the other side. This is very important for brain-machine interfaces, because sometimes you have a very convoluted input signals, but you are only interested into the spectral component, like around 8 Hertz, for example, in epilepsy. Okay, in epilepsy you want the activity at 8 Hertz, all the rest is noise. So with some kind of architecture like this, in principle, in the future, will be possible to route the signals to have the 8 Hertz component on one line, the 20 Hertz component on the other line, and it's all engineering of organic conductive polymers. So this is a job for us, okay? Sorry. Okay, of course, it does work to factorize also electrophysiological signals. So this signal over here is a somatosensory evoked potential in the cortex of a rat model. Okay, so we displace the whisker, and this gives rise to a very high potential in the motor cortex of these animals, and we can factorize it with our architecture. We can send the alpha band on one hand, the beta band on the other one, and some mixed, let's say, configurations. Okay, so this was one idea, the idea of filtering, exploiting the dynamic of the double layer. The other idea that is enabled by this neuromorphic performance of organic polymers is that if they present a specific interaction with some analyte in solution, we can exploit the time evolution of our short-term plasticity to quantify the analytes in the solution. So this is the story that started in 2017. So the STP decay profile depends on ion dopamine concentration. And we can translate this concept in implantable architecture by using deep brain electrodes. These are 80 micron wires that are thought to enter the brain, okay? We can electrodeposit our conductive polymer on the tip by electropolymerizing the monomers. And okay, so we thought it was a piece of cake. So let's measure dopamine in vivo. Okay, it was not a piece of cake, or at least it was the most difficult cakes in the world, because when you enter the surgical room, there are plenty of other problems, because you have additional ground reference. The patient cannot be grounded, for example. And also, you cannot elicit dopamine production by electrical stimulation, because otherwise you will destroy your conductive polymer. You will oxidize it. And so we came up, actually, a brilliant PhD student of mine came up with this architecture. Let's say he reduced the dimensionality of the problem up to a single wire, as if it was a normal working electrode in an electrochemistry experiment. Just pulse it and measure the displacement current in that terminal. Of course, you need a source measure unit to do this. You cannot do it with a normal, let's say, potential stat. But the point is that you can emulate this STP, which is now very resembling a pulsed chronoamperometry. Okay, you can measure the envelope and extract the time constant of your profile, and this actually correlates with the concentration of dopamine in vivo. We did not elicit it by electrical production, but we just carried out a controlled penetration experiment. So you start from the motor cortex of rat, and we go inside with this very, very thin wire that you can see in this picture. I don't know if you can see it, but okay. In the red picture, there is a thin wire. Okay, so you start from the motor cortex, so no dopamine at all. Then you enter the corpus callosum, you have an outburst, and then you enter the substantia nigra pars compacta, which is almost linear increase of dopamine while you're doing your penetration experiment. Okay, so now up to the translational perspective, we are actually developing, and we have developed and authorized by the Italian Ministry of Health, which is a painstaking authorization. We have developed this array of monoelectrode units, let's say. This is a multi-electrode array which can be operated either in recording or in stimulation or in neuromorphic fashion or as transistors, to be placed on the cortex of humans undergoing surgical removal of, let's say, cancer in the cortex of the brain. So, of course, what we told the ministry is that we want to cover the with P.PSS, the electrodes of a neural array, to improve the signal quality, because you increase the capacitance, you lower the resistance, and so this will increase your signal to noise ratio. But of course, this is an excuse, because what we want to study is to improve the spatio-temporal resolution of our transducing capabilities by testing a number of different architectures. So we can improve, let's say, spatial resolution by crowding the array with the recording position, and we can improve the temporal resolution by testing different aspect ratios of our channel, which determine different capacitance, which determine different double layer kinetic. It's always in there, the solution. Okay, so in conclusion, what I wanted to convey you, and I hope that I did it on time, 5 minutes, so we have plenty of time to chatter later. In conclusion, I hope that I conveyed you that OMIEC-based devices, so organic mixed ionic electronic conductor devices, can bridge the signaling gap between the biology and the electronics world, because they are slow, and because they are dependent on ions, as me and you. So we are machines, electrochemical machines, that work on ion and are super slow and very low power, okay? So we need organic electronics to bridge this gap. Thanks to hysteresis, let's say, asymmetry between doping and anti-doping phenomena, these devices are inherently neuromorphic. They are sensitive to ions, so they can be used either to sensing of electrical, let's say, perturbances, or to sense some molecular moieties that I want to have in my solution, okay? That I need to achieve precise control of these time decay phenomena when I'm designing my transduction platform, and I can achieve this control by acting on the architecture, on the operational parameter and on the connectome. So on how do I address and how do I interrogate my system. And the most important thing is that the time-frequency integration provided by neuromorphic organic electronic devices opens up unprecedented possibility in terms of real-time signal processing and filtering, which is, to our interpretation, the key towards more efficient brain-machine interfaces. But this is not the sole application possible. So your fantasy and our fantasy in envisioning future application is the limit, because the field is very young, and so anything that comes up to your mind is very likely that nobody has done it before, and so everything is a discovery, everything is a good paper. If we can do it together, it will be a nice field. Okay, in conclusions, I want to thank all the organic neuroelectronics group, especially, of course, Professor Fabio Biscarini, which allowed me to be here today. This is the entire group. These are the researcher and postdoc. These are the PhD students. This is the organic electronics line. We work together with the people in neurophysiology that are led by Professor Luciano Fadiga, always in Ferrara. I wanted to talk the entire organizing committee, and especially the person of Dr. Manoj Shakavat, which made everything for me to be here, and you for your kind attention. Thank you.
Thank you, Professor. Just one or two short questions, please. From the audience, just one or two short questions, please. Yeah, please, stand up. Introduce yourself and ask.
Hello. Hi, sir. It is a very nice presentation. This is Dr. Penchalaya from VIT University, Vellore, from Tamil Nadu. I would like to know the devices what we develop. What is the mobility of the device? Moreover, they are organic materials you are using for neuromorphic electronics purpose. What is the mobility of the device?
Okay. So the mobility is a quite an elusive concept in this architecture, because in order to extract the mobility, you need to perform a transfer characteristic. You want to fit it, but you want to know a value for the capacitance. Okay, and the capacitance of these hybrid, let's say, very wet electrodes, it's not precisely determined. It's not like we have an OFET, you know, a thin layer of silicon oxide. You see, okay, this is 17 nanofarads per centimeter square, or 14. So we do not have this precision in the determination of the capacitance. So it's difficult for me to give you a number, okay? But I have to say that the mobility, let's say the estimated mobility of P.PSS is usually very, very high. It's like 1 or 2 centimeters square per volt second, okay? Which is 100 times or 10 times more than the best pentasyn we had 10 years ago. So, but I have to say that these numbers are fake, okay? Because they do not take into account the real value of the capacitance, which is the capacitance of a porous electrode, hydrophilic one immersed in an electrolyte. So in our field, we never talk about mobility. We talk about differential transconductance, which is the product of mobility time capacitance, which is something that you can extract unambiguously from the transfer curve of your devices. And this is a number in Siemens, and it's easier to handle, let's say.
Great conversation and great job by Michele. I would like to make one query and one comment here, particularly for the students. If you have carefully listened this lecture, you would have imagined the sulfate ions, organic semiconductors with respect to dopamine. And the question which has been asked with respect to mobility, it should be surpassed with respect to immobilization of the polymeric characterization. If they are doing the polymerization, immobilization, then there is no chance of mobility. But when you are going for the in vivo study, here my question starts. When we are going for the in vivo study, we will have to concentrate on the sulfate ions, particularly they are using the SO3 minus 1 as the immobilized part. So that becomes the more effective in case of dopamine. As a student, if you go for the structural part of SO3 minus, immobilized one and the dopamine, you can concrete the in vivo studies. But when we are going for the in vivo part, can we really find the effect of the or the measurement effect of the SO3 on the mesomerization of dopamine? Because whenever you are taking some deep sound of sleep, you are getting some dopamine here, and this is why the in vivo studies are significant. So before he starts, I must congratulate that this is the next generation work. We will have to have go with respect to the chemical science immobilized and the condensed matter physics.
Exactly.
Thank you very much, Michelle. We can go for the lot of discussion on this, and lot of collaborations are ahead. But your sense of dopamine retrogression with respect to SO3 minus is enormous. I must congratulate you for that.
So, thank you very much.